Hey Team Pika, and welcome to lecture, where today we're going to be wrapping up our discussion of diatomic molecules, this time by talking about heteronuclear diatomics, where the two atoms that form our bond can be different from one another. So a recap of what we talked through in last lecture, we learned that p orbitals, just like s orbitals, can overlap to form molecular orbitals. Because p orbitals have a dumbbell shape, that means that they can either lead to overlap in a head-on fashion, as shown in purple, or a side-on fashion, as shown in green. Both of these produce bonding and anti-bonding orbitals, albeit of different shapes. We also came up with a sort of generic MO diagram for what a homonuclear diatomic molecule would look like, based on the relative energies of the different molecular orbitals that you can come up with from these overlapping p combinations. Just as in previous lectures, if our atomic orbital is our reference energy, the bonding orbital is slightly lower in energy than those atomic orbitals, and the anti-bonding orbital is slightly higher in energy. That's due to the fact that bonding orbitals lead to constructive interference and sharing of electrons, whereas anti-bonding orbitals lead to deconstructive interference and sort of prevent sharing of electrons. Because these side-on overlaps, which leads to a pi symmetry orbital, has less overlap compared to the sigma combination, the splitting in those pi orbitals, so the difference in energy between pi and pi star, is smaller than the energy splitting between sigma and sigma star. What we want to talk about for today, and what's going to motivate today's lecture, is that there are molecules that have different atoms, such as carbon monoxide, and we want to be able to draw these MO diagrams in addition to being able to draw MO diagrams for molecules like O2. Sadly, there can be some nuance when drawing these MO diagrams, and if you look at sort of the final answer for what an MO diagram looks like for a molecule like carbon dioxide, you'll notice that compared to our MO diagram for O2, there's some nuance and some complication here. There's a few areas that I want to highlight. One of those is that you may notice, compared to our diagram for O2, where again it had this nice AO energies, pi splitting a little bit above and a little bit below, sigma splitting below that and above that. Suddenly with CO, we see that the energies of the sigma 2p and pi 2p MO orbitals are switched. The other thing that I want to point out is that whereas before our pi and pi star orbitals had this nice symmetric distribution of electron density around the two nuclei, now in an MO diagram, like for CO, we see an uneven distribution of electron density. Sometimes that electron density seems to be shifted towards the carbon, as in the MO that I've highlighted in purple, and sometimes, as in this MO that I'm about to highlight in orange, sometimes the MO electron density seems to slightly favor the oxygen and to be centered more around that oxygen, as shown in orange. And so if we're truly going to understand this MO diagram and be able to draw MO diagrams for molecules like carbon monoxide, we need to understand where these nuances and complications and discrepancies are arising. And so that is going to be the subject of today's lecture. How is it that we can take a molecule like carbon monoxide and dig into the fundamentals of what factors, beyond those that we discussed last lecture, dictate the shapes and the energies of the molecular orbitals and lead to differences compared to what we saw with O2. And so with that, let's go ahead and get started. So I'm going to start off fairly abstract for today. It's going to be a little bit mathematical. For those of us for whom mathematical explanations are really helpful, I look forward to working through this process with you. For those that like slightly more pictorial or conceptual representations, I'll bring always back the math to those pictorial/conceptual representations. And so those would be, if you're in that boat of being more of a pictorial and more of a visual learner, where I would focus your attention for today. So this Lecow MO theory, we said way at the beginning of our discussion that what a molecular orbital is a linear combination of the wave function on atom A and the wave function on atom B. For homonuclear diatomics, we restricted our discussion to saying that the coefficients in front of the wave function for atom A and the wave function for atom B should be the same because there was no difference between the two atoms. We're going to now relax that restriction and see what in general can tell us the relative weighting between coefficient A, which tells us how much time the electron is spending nearby atom A on A's wave function, and how much of its time it should be spending on atom B, dictated by the magnitude of CB. Now, a nonpolar bond, remember, has these two coefficients equal, and in the opposite extreme, if we were in a situation where we had a purely ionic bond, in that case, A plus B minus would have the coefficient on A be 0 because the electron is spending none of its time on the cation, and CB equals 1 because the electron is spending all of its time on the anion. For situations in between, like with polar bonds, we can use a technique called the variational principle to solve for the optimal coefficients Ca and Cb. And the factors that go into determining that solution are twofold. The first factor is what are the atomic orbital energies themselves. In this discussion, so that it uses the same notation as Atkins, instead of calling these E sub A and E sub B, I'm going to start to use the language alpha sub A and alpha sub B to talk about these orbital energies. Both alpha A and alpha B have overlap integral style expressions that you can define them precisely mathematically, but for our purposes, these are just our orbital energies for our atomic orbitals that we're used to. The second quantity that we're going to need is something called a resonance integral. And very approximately, as I put it on this diagram, that resonance integral corresponds to how much energy stabilization we get due to the overlap of the two atomic orbitals to form a bonding molecular orbital. There's a couple of limits that are good to know for this resonance integral. One being that if the two atomic orbitals don't overlap at all, or don't overlap in such a way as to lead to a net constructive or a net destructive interference, then beta is going to equal 0 because there's no net overlap between the atomic orbitals. Otherwise, because beta refers to a stabilization, you can expect beta to be a negative number. Now, I won't walk us through the process today for solving for the coefficients according to the variational principle, but I will present the final results. The approximate solutions to this linear combination of atomic orbitals is that we have a set of anti-bonding orbitals, which are going to be given with the negative subscripts, and then we also have a set of positive orbitals given by these positive subscripts. And these solutions look somewhat complicated. We have, for example, with our energy expression, that the energy of the anti-bonding orbital is equal to the energy of whatever the orbital is on atom A minus beta, that stabilization energy component, times the cotangent of some variable zeta, or squiggle if you like, which in turn has a lot of variable dependence on beta and on the difference in energies between the two orbitals. Similarly, you'll notice that this zeta parameter comes into play because it tells us what our relative coefficients are between our antibonding wave function and bonding wave function for what fraction of the electron density do we expect to be related to atom A's wave function, and what fraction of the time is our electron spending its time on atom B. Taken by themselves, this set of expressions is not necessarily very intuitive, but it's really useful for helping us understand the behavior of these MOs in general. So what we're going to do is we're going to explore 3 limiting cases of what zeta, beta, or alpha is equal to help us understand some guiding principles for MOs and what types of bonding and anti-bonding combinations can form. So the first limiting case that we're going to study is when zeta goes to 0. Looking at our expression for zeta and looking up some trigonometry rules about how cotangent works, as zeta approaches 0, or at least becomes very small, this cotangent expression is going to simplify for us. And in fact, because cotangent simplifies, we can then plug in our new value, our simplified value for cotangent, into all of these expressions. And after you work through the algebra, you'll notice that the energy of the antibonding orbital simplifies to simply be the energy of the orbital on atom B, the atomic orbital on atom B. Our other wave function simplifies to be the energy on atom A. And then looking at the wave functions, these wave functions have also simplified back to just the original AO wave functions. And so when zeta equals 0, it's sort of as if nothing has happened. We've tried to combine two atomic orbitals together to form new MOs, and we just had spit back out the original ones. So in a sense, factors that cause zeta to go to 0 yield a set of what mathematically you could describe as MOs, but chemically you would just describe as the original AOs because they have the same energies and same wave functions as what the isolated atoms looked like. Another way to put this in a little bit more chemically intuitive words is that anything that causes zeta to go to 0 is going to prevent an MO from forming. And if zeta goes to 0, that means that our chemist's language for describing these orbitals should be to describe them as atomic orbitals, not as molecular orbitals, because really there's no difference. So what that means for us is we need to now dig into, well, what factors cause zeta to be 0? Zeta is equal to half inverse tangent 2 times the magnitude of beta divided by the difference in these AO energies. And so zeta goes to 0 either when beta goes to 0 or when the denominator term becomes really big. So what that means for us chemically is that we can explore what happens, what would lead to beta going to 0, or what would lead to our difference in AO energies being very large. Where would we expect to see that? The first case, some situation that would lead to beta equals 0, is when you try and overlap together two orbitals that have different symmetry. As it turns out, two orbitals that have different symmetry, when you attempt to combine them together, leads to a region of space with positive overlap, shown here, and then similarly a region of deconstructive overlap, shown here. Because the symmetry of this problem is such that the amount of constructive interference is exactly canceled out by the amount of deconstructive interference, there's no net overlap. Trying to combine together an s orbital and a px orbital leads to beta equals 0, and hence these two atomic orbitals cannot combine to form a molecular orbital. So it's no coincidence that in the last lecture, as I was walking us through and enumerating all the different ways that atomic orbitals could combine to form molecular orbitals, that we didn't even consider this type of MO combination on our list. It's because this does not form an MO, and we don't need to consider it any further. A takeaway for us should be that atomic orbitals must have compatible shapes to produce bonding and antibonding MOs. AOs with incompatible shapes will not lead to net constructive or net destructive interference, and they can't form molecular orbitals. And so that's actually a really good thing for us because it means that we don't need to consider all possible combinations of atomic orbitals to form our molecular orbitals. We only need to consider types of orbitals that can have a correct shape in order to overlap in such a way as to have net constructive or net destructive interference. And to make this concrete, I presented a couple examples of types of orbitals that can overlap that have compatible shapes. You'll notice that the first two of these combinations are ones that you've already seen in lecture. We started off our discussion with MOs in terms of talking about these sigma or sigma star combinations when two s orbitals overlap. So that's shown at left. And then we also talked about the combination that could form when two p orbitals overlap in a side-on fashion. But Compatible shapes could also include new combinations that we haven't seen so far in lecture. And one that I want to highlight because it'll become relevant for us pretty soon is this overlap of an s orbital and a pz orbital to form a new type of sigma MO. In fact, you call this would be like an sp mix of a sigma orbital. And then some examples of incompatible shapes would be just like the one that I've just shown, an s orbital attempting to mix with a px orbital, or a pz orbital trying to mix with a px orbital. In both cases, the amount of constructive interference is exactly canceled out by the amount of deconstructive interference. And so that's why these have incompatible shapes and cannot mix to form a molecular orbital. All right, so not only beta matters for trying to come up with limiting cases where zeta would go to zero and hence we don't form molecular orbitals, but also zeta is going to go to zero in the case where our atomic orbital energies and the difference between them becomes large compared to beta. And a good example of this would be something like a 1s orbital on carbon, atom A, trying to mix with a 2s orbital on carbon, still atom B. These two orbitals do not mix with one another to form an MO because the 1s orbital is vastly more negative in energy compared to the 2s orbital. And so, just like you saw on some of your computational chemistry calculations or in the lab that we've been doing paired with this lecture course, the core orbitals and the core electrons don't mix in any appreciable way with the valence orbitals or the valence electrons. And this expression helps us understand why. It's because MOs don't form if the difference between alpha A and alpha B is too large. Okay, so we've tackled this case where zeta goes to zero. Now let's tackle the opposite case. What happens when zeta gets as large as it's going to get, which ends up being pi over 4? So how we would get to this value is in a situation where actually the denominator of this inverse tangent argument becomes as small as possible, becomes 0. So if this term blows up because my two AO energies have the same energy, then you get that zeta is equal to 1/2 inverse tangent times an extremely large number. Our inverse tangent function, as x gets really big, asymptotically converges to pi over 2. And so that's going to give us a value for zeta of, for our inverse tangent part of the argument, of pi over 2, giving us ultimately zeta equals pi over 4. So this is our situation from last lecture. Orbitals with compatible symmetry and identical AO energies are going to combine together to form bonding and anti-bonding combinations. In this limit, cotangent of pi over 4 is equal to 1, and hence our bonding orbital is going to be the energy of the AO plus this beta stabilization factor. Remember, beta is negative, so plus beta is going to lead us downhill in energy. And then similarly, our anti-bonding orbital is going to be the opposite. It's going to have this beta stabilization, but minus beta to raise us up in energy. And like we were used to in our homomolecular case, we have that our bonding and our anti-bonding wave functions are either the additive combination of A and B or our subtractive combination of the two, both with equal coefficients, so that the electron we have an electron density for our orbital that is equally weighted and symmetric between the two combinations. And so kind of where a lot of interesting chemistry lies is somewhere in this intermediate region. What happens when zeta is bigger than 0 but less than pi over 4? In other words, what happens when our two orbital energies are not identical to each other, but there's still some overlap and some energy stabilization? In this case, I'm going to draw you qualitatively what this MO diagram looks like. You'll notice that we still have a relative ordering where our bonding orbital is lower in energy than all of the atomic orbitals, And our antibonding orbital is higher in energy compared to all of our atomic orbitals. The energy of the bonding orbital is closer to the AO energy for atom A, and the energy of the antibonding orbital is closer in energy to the AO energy on atom B. We can take a look at what our wave functions look like, and what we know, because of how sines and cosines work, cosine zeta and sine zeta, where they would be equal is at pi over 4. So if we're closer to 0, that means that this sine zeta is going to be smaller than cosine zeta. And so how I'll represent that is I'll kind of put in for sine zeta a coefficient C1, I'll put in for cosine zeta a coefficient C2, and to help me remember that this cosine term is larger in magnitude than the sine term for these intermediate cases, I'll go ahead and capitalize C2 so that we can see that there's a non-symmetric wave function such that in our bonding wave function, there the wave function has a larger character, or the electron is spending more of its time closer to atom A, versus on our antibonding wave function, there that wave function has more character of atom B. And so let me go ahead and annotate then our generic MO diagram in the case where we were talking about the combination of two s orbitals. Different atoms though, so the s orbitals have different energies. In this case, my bonding wave function is still going to look like the additive combination of two s orbitals. However, the electron density centered around atom A is going to be bigger than the electron density centered around atom B. Similarly, for my antibonding combination, now my wave function has more character related to atom B, and so my sigma star combination is going to look like as before in terms of shape, but it's not going to look symmetric. So my MO diagram and the shapes of these wave functions are going to look a little bit more as I've drawn them here than they would in the symmetric case. And that's all due to the fact that for heteronuclear systems, our atomic orbitals do not have the same energy, and so we don't end up with symmetric looking wave functions. Now that we've covered these general principles, let's go ahead and try and bring this to a concrete example so you can see both what the computational chemistry results would be for a heteronuclear diatomic molecule and some of how these abstract principles work out in practice when we go to draw the MO diagram for a real molecule. So the molecule we're going to tackle is HF, hydrogen fluoride, and one of our orbitals, it's really easy to know how the hydrogen is going to contribute to the bond. The only orbital it has is a 1s orbital. For fluorine, though, fluorine has a 2s orbital, a 1s orbital, a 2s orbital, and 3 different types of 2p orbitals. And in our MO diagram, we really need to know which of those many different types of orbitals is going to combine with the 1s orbital on hydrogen. So what I'd like you to do at this point is go ahead and pause the video and try and answer the following question. Of the different types of orbitals that are available to fluorine, again, there's 4 different types, 1s, 2s, 2px, 2py, and 2pz. Excuse me, that's 5 different types of orbitals. So for our 5 different types of orbitals, which have the right shapes or the compatible shapes to be able to form an MO with hydrogen? Go ahead and pause the video and answer the question, which of fluorine's atomic orbitals have the right shape to combine to form a bonding and an antibonding MO with hydrogen's 1s orbital? So the answer to this question is that there are 3 types of orbitals on fluorine that have the correct shape. One is the 1s orbital. Another orbital with the correct shape would be the 2s orbital on fluorine. And last but not least, the 2pz orbital also has the correct symmetry and shape to be able to form bonding and antibonding orbitals with hydrogen. In my drawing here, I've only shown the bonding combinations, but hopefully you can see for yourself that if we can form a bonding combination, by definition, we can also form that antibonding combination. So where we need to look to figure out which of these three different contenders for our MO actually forms a bond with hydrogen is that we need to look at what the atomic orbital energies are for fluorine. And we need to find which combination is closest, or which orbital on fluorine is closest in energy to the 1s orbital on hydrogen. On this diagram, I haven't even attempted to put on this diagram fluorine's 1s orbital because it's so low in energy that it extends way farther beyond the diagram. But what you can see is the 2s orbitals, which are shown here according to this curve. You can see that fluorine's 2s orbital is negative 40 eV in energy, eV being yet another unit system for our energies. And then also our 2p orbitals are shown. And here, by the time we get to fluorine's AO energy for the 2p set of orbitals is negative 18.6 eV. And what I also want us to note as a general trend, because it'll be very helpful when you're drawing your MO diagrams, notice that as we go left to right along the periodic table, within a period, more electronegative elements have lower atomic orbital energies. And hopefully you can connect that back to an earlier part of our lecture series where we talked about how as you go left to right along the periodic table, Z effective increases. And so the stabilization of these orbitals gets bigger and bigger as there's a more concentrated nuclear charge. And so to bring things back to our MO diagram for HF, it's going to be the 1s orbital on hydrogen and the 2pz orbital on fluorine that have the best energy compatibility to be able to form an MO. And so that's how we're going to construct our MO diagram. Any orbitals on fluorine that don't combine with the 1s orbital on hydrogen, we will leave alone and we will treat them as so-called non-bonding orbitals. So I've only drawn the valence electrons in my diagram, which is pretty typical since the core electrons don't contribute to bonding. They kind of just hang out by themselves. And our 2s orbital on fluorine, since it is not going to combine with the 1s orbital on hydrogen, we're going to just drag into our MO diagram. It doesn't disappear. We need to conserve the number of orbitals that are available to us, but it simply gets left alone. So my first type orbital, we still could call it 1 sigma to say that it's the first sigma orbital that shows up in our diagram, and we can depict it as simply being the 2s orbital on fluorine, but it's a non-bonding orbital because it did not have its energy either stabilized or destabilized by the presence of this hydrogen. Similarly, we determined that 2 of our p orbitals have incorrect symmetries to be able to form bonding and antibonding combinations. In particular, those orbitals that don't have the right energies to form a molecular orbital are the 2px and 2py orbitals. And so we'll go ahead and label these as having pi symmetry. And what they're going to look like is sort of lone pairs on fluorine. Let's see if I can find a good spot to draw on. So here we've got our 2px orbital on fluorine. And similarly, degenerate in energy, but different in orientation, would be this 2py combination, which is going to come in and out of the plane of the board. And so I'm going to do my best to draw that in 3D. And it'll look something like this. Great. So now that we've drawn all of our non-bonding combinations, we can now try and depict the bonding and anti-bonding combinations that form as my 1s orbital on hydrogen interacts with my 2p orbital on fluorine. So one of my bonding combinations, my only bonding combination is going to have a shape that looks like so. I'm going to depict my two nuclei. We have the 1s orbital on hydrogen overlapping with the 2pz orbital on fluorine. And you can either draw these kind of depicting the overlap directly, or you can try and clean this up and draw it more like a boundary surface diagram, like what we've been doing. In which case, your orbital might look a little bit more like this. Since this orbital has sigma-type symmetry, because it's cylindrically symmetric, we're going to go ahead and label this as another type of sigma bonding orbital. And in this case, I'm going to put a number 2 out in front because, again, it's a little bit hard to label these with subscripts. I maybe could do that as S and P, but at some point, if the orbitals are too complicated, we just number the orbitals in terms of their symmetry, and then increasingly large numbers as we go up in energy, similar to how your n quantum number works for atomic orbitals. Okay, and last but not least, we need to draw in our antibonding combination. And this antibonding orbital is going to look very similar to our set of bonding orbitals for fluorine, just a little bit different. So in this case, the antibonding orbital has more hydrogen character associated with it, since hydrogen is the orbital that's closest in energy. So I'm going to attempt to draw the hydrogen part very large and my fluorine p orbital very small in order to exaggerate but show what this combination looks like. And we can label this as an antibonding orbital. And as I'm thinking about it, I tried a little bit to draw my hydrogen as being smaller on my bonding orbital, but let me try and make that just a little bit more exaggerated for us. So the wave function character on my hydrogen in the bonding orbital is very small compared to the wave function character of my fluorine in the bonding orbital. And so I think this picture draws that a little bit more cleanly. There we go. And then, as always, we try and draw connecting lines to show that this antibonding orbital is formed from a combination of my 2p orbitals on fluorine and the 1s orbital on hydrogen. And we'll also depict that my bonding combination arises from an overlap of the 1s orbital and those same 2p orbitals. And there you have it. Our last step for hydrogen fluoride would be to populate these MO diagrams with the appropriate set of electrons. And we can do that using our standard chemical principles for drawing these diagrams. So in this case, hydrogen has 1 electron to start with. Fluorine has 7 valence electrons. And so in total, our molecular orbitals will have a total of 8 electrons between them. 2, 4, 6, 8. And so what we can see is that in hydrogen fluoride, we have a bond formed between our HF and we have some electron density present on these non-bonding orbitals. Okay. And what's really interesting to note is that this means that if I look at my molecular orbitals from the results of a computational chemistry calculation, that the diagram really looks very similar. We can see that our wave function character is especially exaggerated on this 3 sigma orbital. I guess they labeled theirs implicitly with the 1s orbitals being the core electrons. So let's go ahead and relabel this so that we're consistent with them. And so you can see on this molecular orbital diagram for HF how our wave functions and the electron density is not symmetric between the two atoms because our bonding orbital has more character related to the lower energy set of atomic orbitals, and our anti-bonding orbital has more character related to the higher energy atomic orbital. We could also go ahead for HF and calculate a bond order, and the reason that it's helpful to do this is because this is our first time seeing non-bonding orbitals, and it's important to note that non-bonding orbitals do not contribute to our bond order calculation. So the bond order for HF would be 1/2 times 2, the number of electrons in bonding orbitals, minus 0, because there are no electrons in this case that are present in anti-bonding orbitals. And that gives us a bond order of 1, which matches what you would expect to see based on your MO diagram for your Lewis structure for HF. Okay. And hopefully you're able to see from us drawing this MO diagram our big takeaway, which is that in a heteronuclear MO diagram, the more electronegative element will have the lower energy valence atomic orbitals, and hence the bonding orders will be closer in energy and wave function character to the more electronegative element. The opposite is true for the antibonding orbital. In this case, our antibonding orbital is closer in both energy and wave function character to the more electropositive element. The other thing that we can do is we can start to draw some connections between what we learned with this HF diagram in order to talk about the MO diagram for carbon monoxide, the original MO diagram that we started off today's discussion with. 2 things that I want to know. First, a comment in blue that because oxygen is more electronegative than carbon is, we're going to draw all of our oxygen AOs lower in energy than our carbon AOs. This is because oxygen has a higher Z effective, and so all of those orbitals feel a stronger pull to the nucleus and are more stabilized relative to the atomic orbitals on carbon. A second thing that I want to notice, especially in an MO diagram where we're starting at this point to draw many, many lines, is that still our bonding orbitals are always lower in energy than our atomic orbitals, and our atomic orbitals are always lower in energy than our anti-bonding orbitals. Secondly, I want us to look at this comment in purple. Focusing on our pi and our pi star orbitals, notice that there is increased electron density in the pi bonding orbital, and there is on the oxygen, and also notice that there is increased electron density on the carbon in the pi star orbital. That is as a direct result of how our wave function character becomes non-symmetric when our atomic orbital energies differ from one another. So that's all well and good. However, I still don't think that we have fully solved the question of why does the CO-MO diagram look the way that it does? Because as I see it, this 3 sigma star orbital still looks complicated, right? It appears to not exactly look like this sigma star combination that we were used to for our homonuclear case. Same thing with our 2 sigma star orbital. In some ways it looks like a combination of 2 s orbitals combining deconstructively, but it almost looks like there's a little bit of p-type character on this oxygen. And so in order to understand where these slightly more complicated MO shapes are coming from, we're going to have to talk about an effect or a phenomenon called second-order mixing. Second-order mixing is the idea that MOs of equivalent symmetry, assuming they're close in energy and therefore have compatible enough energies to be able to combine together, that those MOs of the same symmetry can combine to form new molecular orbitals. Where this is really important is for the two orbitals that have the same symmetry that are close in energy in a diatomic molecule in the second period. Namely, when we have our sigma 2s star and our sigma 2p orbitals. For an element like, say, fluorine, where the 2s and the 2p orbitals are very different from one another in energy, you won't actually see any of this sp mixing. And so you'll notice that the MO diagram shown to the left is exactly the same as the MO diagram that we drew for oxygen last lecture. The reason for this is that in oxygen, those orbitals are too far apart, not necessarily for there to be no second-order mixing, but for there to not be enough second-order mixing for there to be any appreciable changes in the relative energies of our molecular orbitals. Where things become complicated and interesting is for atoms that are closer to the left-hand side of the periodic table, like lithium, beryllium, boron, carbon, and even nitrogen. In these cases, when our sigma 2p and our sigma star 2s orbitals overlap with one another, the net effect is that this sigma 2p orbital raises up a little bit in energy, and the sigma 2s star orbital goes down a little bit in energy. This is net stabilizing for the overall molecule, but it does mean that if there's enough second-order mixing, that we're going to swap the relative energy orderings of my pi 2p and my sigma 2p orbitals. And I think that it's best to see how this works in the actual atoms themselves. And so the first thing I want us to do is notice that as we go left to right along this periodic table, that the 2s orbitals decrease in energy at a far faster rate than the 2p orbitals do. That means that for an atom like carbon, there's a fairly small split between the 2s and the 2p orbitals, versus an atom like fluorine, where there's a very large split between the 2s and the 2p electrons. As a result, you can plot how the MO diagram changes for different for different homonuclear diatomics going left to right along the periodic table. And what I want you to notice is that as a result of second-order mixing, while all of these orbital energies are slowly getting more and more negative as we go left to right along the periodic table, this sigma g2p orbital is changing more rapidly than any of those. And so while it starts off for elements where there's a large split between the 2s and 2p orbitals and hence no appreciable second-order mixing, starts off in an element like fluorine or neon below the level of the pi 2p orbitals, by the time we get to the left-hand side of the periodic table, those relative energy orderings have switched. And where that switch occurs is somewhere around between nitrogen and oxygen. For oxygen, sigma g is lower in energy than pi 2p. And for nitrogen, N2, now suddenly this sigma g has had enough second-order mixing to be raised up in energy a little bit above these pi orbitals. This second-order mixing effect also explains the energy orderings in our carbon monoxide molecule. So you'll notice that second order mixing has caused our sigma orbital to go up a little bit in energy, and also helps explain why this bonding orbital that I've boxed in purple gives our sigma 2 sigma star orbital a little bit of p-type character on the oxygen, and why our 3 sigma orbital on this carbon has not only p character on the oxygen, but a little bit of s-type character on the carbon. And so second order mixing has an overall effect that in some cases can lead to different relative energy orderings between our orbitals, and also makes the shapes of our wave functions a little bit more complicated and a little bit more interesting. In this class, I don't necessarily expect us to be able to draw these subtle SP mixing effects when it comes to the shapes of the wave functions, but I do want us to be able to recognize where these shapes from a computational chemistry calculation come from, and when they look a little bit different from expectation, to recognize that that's probably an effect of second order mixing. And so with that, that is all that I have to talk about us with today. So let's bring things back and summarize what our most important takeaways are when it comes to thinking about MO diagrams for arbitrary diatomic molecules, both homonuclear and heteronuclear. Our first important takeaway is that forming MOs comes about as a linear combination of atomic orbitals, but not all atomic orbitals are equally able to form MOs. To form molecular orbitals, atomic orbitals must have compatible shapes, having the same symmetry, and they must be of similar enough energies to lead to appreciable mixing. Our second big takeaway is that when MOs form in a heteronuclear diatomic molecule, the bonding MO is closer in energy and shape to the more electronegative element, which remember has lower atomic orbital energies, and the antibonding orbital is closer in energy and shape to the less electronegative element. And so were you to draw an MO diagram depicting how two s orbitals would overlap in a heteronuclear diatomic, you want to make sure and draw the shapes of the MOs not symmetric in terms of the electron density on atom A versus atom B, but actually fairly non-symmetric, such that in our bonding orbital, most of the electron density is present on closer to atom B, and in our antibonding orbital, most of the electron density is closer to atom A. Our third takeaway, and final takeaway for today, is that for diatomic molecules, second order mixing can occur, and the rule of thumb that we'll use in Chem 346 is that if our diatomic molecule involves any of the elements B, C, or N, we're going to predict that second order mixing will occur to a significant enough extent that the energy orderings of our molecular orbitals is going to be pi lower than sigma for the bonding combination, rather than the usual sigma lower than pi. And so with that is all that I have for us today. I hope that you were able to see a little bit more insight into what molecular orbitals look like for diatomic molecules, and that'll set us up really nicely for talking about bigger systems in the next upcoming lecture, as well as tying this back to how we can learn about chemical reactivity via these MO diagrams. So with that, I look forward to seeing you all in class. Take care.